Chapter 3, Section 4 of your textbook talks about multiplication of whole numbers. And throughout that chapter, you'll look at various models of multiplication, some of the properties of multiplication, how to use those properties to help develop computational strategies for students, multiplication algorithms, how to use them, including the standard algorithm. We are not going to talk about multiplication with number bases other than base 10, but that is covered in your textbook. And then mental multiplication skills and estimation techniques. So we can model multiplication in several different ways, and it's important that we do. I mentioned this with sort of in passing in past videos. I don't think anyone who studies mathematics education would argue that learning multiplication facts isn't important. I think there's a misperception out there that researchers think that it's not important or that teachers these days don't think it's important. That's not true. We know that multiplication facts, knowing them, memorizing them, does help later performance in math. It makes things easier. It is quicker to know that 8 times 7 is 56 than to plug 8 times 7 into your calculator. It's better still if we understand multiplication though, so we can also realize that 80 times 7 is 560. So that we could understand that 10% of 560 is 56, which means that 5% would be half of 56, or 28. And that 15% would be 56 plus 28, or 84. All of those sorts of mental arithmetic rely on knowing basic facts. But it's more than that. It also relies on being able to work mathematically, being able to understand, maybe sometimes just intuitively understand, but to understand how mathematics works. To get there, it's important that rather than just have students memorize facts, rather than just have them follow an algorithm mindlessly, we help them explore and understand how those things work. And so one way we can describe multiplication to students is as the idea of repeated addition. Multiplication can be thought of as repeatedly adding the multiplicand, multiplier times. Let me talk about multiplicand and multiplier. When we multiply two numbers together, like 7 times 5, one of these numbers is considered the multiplicand, and one of these numbers is considered the multiplier. However, you don't need to know that. You don't need to worry about that. And the reason is, at one point in elementary school, those terms were specifically taught, and they might still be in places. But no one can agree on which is which. And I know this because I searched for it a couple of years ago when I first started teaching this course. There are some sites that would say this is the multiplicand, and there are some sites that would say the 5 is the multiplicand. Don't worry about it. Unless your curriculum makes you teach your students, think of these as factors. Multiplication is repeated addition, but it doesn't matter which way we repeat it. In other words, this is the same as 7 5 times or as 5 7 times. This is 7 plus 7 plus 7 plus 7 plus 7. It's also the same as 5 plus 5 plus 5 plus 5 plus 5 plus 5 plus 5. In either case, multiplication is repeated addition. The 7 and the 5 are factors. Two factors multiplied together give us a product. The terms you should know are factors and product. Again, if you have a future textbook, if your math methods textbook specifies multiplier and multiplicand, or your math methods teacher does, then by all means, use that information. But even though this particular PowerPoint still uses these terms, I have a feeling it's because the PowerPoint is from an older edition of your book. Because when I saw this, I looked up those terms and I can't find them in your textbook. I might have missed them. But it's old-fashioned language. And I just say it's old-fashioned not because it's not important, except it isn't important really anymore. It's not like subtraction where minuend and subtrahend might still be used. Multiplication is commutative. 7 times 5 is the same as 5 times 7. So multiplicand, multiplier, for our purposes, we don't have to worry about it. Know them as factors. And understand that it is repeated addition. So if we say 4 times 3, I like to think of this as multiplication. The multiplication sign means of. We talked about that a little bit when we talked about other bases. And so what I do like to think of this as is 4 groups of 3. So that would be 1 group of 3, 2 groups of 3, 3 groups of 3, 4 groups of 3. But it's equally correct to look at this as 3 groups of 4. Both these sentences are correct. Both represent this multiplication sentence. Another way we could picture multiplication is as an array or an area. Your textbook gives some nice picture examples of both of those things. If we're looking at an array, we're looking at sort of the intersection points on a grid or with crossed craft sticks or something like that. It also could be used as area when we look at the area of a rectangle is length times width, which is multiplication, right? 4 feet times 3 feet is 12 feet squared. Could also be modeled as a Cartesian products, and Cartesian products are described in your textbook, and take a look at how they are represented. That isn't used as much in elementary schools, in my experience. Both of the other approaches are, and often arrays and area models are looked at as 2 separate approaches, even your book just happens to combine them. So here we have 4 groups of 3 brushes. Again, we have 4 groups of 3, that equals 12. We could model other types of repeated addition. We can model it using colored rods. Colored rods are usually Cuisenaire rods, but they don't have to be. Cuisenaire is a specific brand. It's a registered trademark of somebody. It's what's most commonly used, but there are other models out there as well. So here we see we have 5 groups of 4. So 1, 2, 3, 4, 5, and then we could line up above them the rods of length 10 to see really easily that those equal 20. We could also do it on a number line, and that's what the bottom part of your screen is showing right now. Again, this is showing us 5 groups of 4. So our first group of 4 moves us 4, our second group of 4 moves us 4, and so on. Certainly, having students count by different amounts is one way to help them understand multiplication, as well as understand multiples of things. Not a bad strategy at all, in my opinion. So here we have a formal addition and multiplication of whole numbers as repeated addition. If we have some natural number, remember a natural number is 1, 2, 3, 4, 5, etc. So for any whole numbers a, and an whole number includes 0. So 0 could be a whole number, but it's not a natural number. So n times a, like 5 times 1, or 5 times 2, or 3 times 0, is going to be n number of terms. Here is on the left-hand side is what an area model would look like to show 4 times 5. You'll notice we have 4 lines going horizontally. Those might be just lines. They might be some sort of manipulative. Again, craft sticks are commonly used. Other things might be used as well. And then we have 5 lines going vertically. The intersections of those lines, when we count them, that gives us what 4 times 5 is. So 20. The right-hand side, you see an area model where we have something of length 4 units and width 5 units, and we divide that into equally shaped blocks. We see that that is 20 units, showing us sort of geometrically that 4 times 5 is 20. It's just that it's 20 square units, not 20 units. Here's an example of the Cartesian product model, which is really what you might have done. If you took math for liberal arts, you probably learned about the fundamental counting principle when you learned about permutations and combinations and stuff like that. That's very similar to the Cartesian product model, which is also sometimes called the fundamental counting principle or the multiplication principle. Suppose you want to take 2 web courses besides this one, and you can take either world history or ancient history as one of the courses. And your other course, you're going to take one of the languages of Latin, French, or German. And because they're online, there's no schedule conflicts. So we can use a tree diagram to demonstrate the possible schedules we could have. So looking at a set, we have our set H for history of world history, ancient history. Notice how it's in braces. And set L as a foreign language. Notice that too is in braces, Latin, French, or German. Showing this as a tree, here's what it looks like. So we have world history and ancient history. And it doesn't matter what we start with. We could have started with languages rather than started with history. So if I choose world history as my first course, then my second course is going to be Latin or German or French. So my combination of courses there are world history Latin, world history German, world history and French. Or if I choose ancient history as my first course, then my second courses could be Latin or German or French again. So my choices there are ancient history Latin, ancient history German, ancient history French. And so I can count and I see I have a total of 6 possible schedule combinations. This is that fundamental counting principle. Whenever you have a series of choices, you can multiply the number of choices you have each time together. So I had 2 choices for a history course and 3 choices for a language course. 2 times 3 is 6. I have a total of 6 choices. And that is true for any finite sets. We aren't going to worry about infinite sets in this course. But if the cardinality of set A is A, so there are A items in set A and B items in set B, then the cardinality of those sets is A times B, where times here is the Cartesian product. We talked about the closure property and we talked about addition. Multiplication is also closed for the whole numbers and for most other things. If you multiply 2 whole numbers together, your answer will be a unique whole number. Multiplication, as we know, is commutative. Order doesn't matter. So for any, and that we're again speaking about whole numbers, but this is true for many types, not all types, but certainly all types of multiplication we teach in elementary school. So if we know that 2 times 7 is the same as 7 times 2. 85 times 3 is the same as 3 times 85. There's also the associative property. In other words, we can group factors that we're multiplying together however we like. The identity property, we have a unique number. It's the number 1. That's the identity element. That for any whole number, that number times 1 is that number. So 5 is the same as 5 times 1 or 1 times 5. And we have what your book calls the multiplication property of 0. Other books call the 0 property or something else, other terms for it. For any number times 0 is 0. 0 times any number is 0. So 7 times 0 is 0, which is the same as 0 times 7. So we could display that here. On the left, we have an example of 3 times 5. On the right, we have an example of 5 times 3. In terms of associative property, here we have, we always do parentheses first, remember. So we have 5 times 4, that's this flat piece. And then we have 3 of them, that makes 60. Here we have 3 times 5, that's this flat piece, and we have 4 of them. So we have 15 times 4, that also makes 60. They're the same. And you might recall from pre-algebra and algebra the distributive property. Increasingly, we're teaching these properties in elementary school, not necessarily explicitly, but in ways that help prepare students. for pre-algebra. This is controversial. I know the Common Core state standards are controversial. Personally, my personal opinion as an educator is that there's both good and bad behind them. I find that most of their critics are over exaggerating their problems, and most of their supporters are under exaggerating their issues. Um, One of the things that sometimes gets shared on Facebook or other social media is there is an example of kind of a complicated multiplication problem that shows something like you see on your screen that's really showing the distributive property. And someone is basically saying this is ridiculous. And as soon as I saw it, and one of my friends who still teaches middle school math, or who did until a couple years ago, did when she saw it, thought the same thing. She actually responded and said, if everyone in elementary school did this, it would make pre-algebra or just middle school math in general, especially 7th and 8th grade middle school math, so much easier. So keep that in mind. Sometimes something is a little trickier. It might be harder to teach and harder to learn, but it has huge benefits down the road. That's not just true in math, it's true in other subject areas as well. So we always want to look at the big picture, which is one reason why you take math beyond just the level of math you're teaching. So here what we see is, looking at sort of an area model, is that the area of the large rectangle is the same as the sum of the two smaller rectangles. We can break them apart. We do stuff like this in geometry too, right? When we try to find the area of a shape that's complicated, we break it up into simpler shapes. It's kind of similar. And of course, in algebra, where we would not show it like this in elementary school, we introduce the distributive property like this. We know that A times B plus C is the same as A plus B plus A times C. One thing that students sometimes don't recognize is that the commutative rule is still true here. So it's also equally valid to say B plus C times A equals A times B plus A times C. Equally valid. Multiplication is also distributive over subtraction, and that makes sense because subtraction is just the inverse of addition. So it's distributive over addition, it must be distributive over subtraction. That difference doesn't always specified, and that's okay too. I mentioned that already. We talked about, and the distributive property doesn't have to be for just two terms. It could be for any number of terms. So A times B plus C plus D is A times B plus A times C plus A times D, and so on. We could have it for 5 terms or 12 terms or 50 terms if we wanted. You probably remember factoring from algebra class, and all factoring is really using the distributive property, sort of working backwards with it. So if we start with AB plus AC and then we say, oh, that's the same as A times B plus C, what we've done is we've done some factoring. We see that the factors here of AB plus AC are A and B plus C. So in this example, we want to use an area model to show this little more complicated example. This is FOIL. You remember FOIL probably from algebra class in high school or other. First, outside, inside, last, and that's exactly what they've done here. We want to show this using an area model. And x times z is xz, x times w is xw, x times y is yz, or sorry, x times y is not yz, y times z is yz, and y times w is yw. And so down here we see x plus y, and across we see z plus w. Again, you would not model something this complicated in elementary school, but understanding that it works and sort of how it works is beneficial for you because you're helping prepare your students for future math. And hopefully math teachers in middle school, as they start teaching pre-algebra, do model things this way so that algebra becomes more than just a series of rules and that students develop better understanding for that. So we can use the distributive property. So now we're using more algebra rather than geometry, or we're using logic rather than vision to show that these two things equal each other. And so what we do is each time we do it, we explain what we're doing. So for step 1, it's the distributive property of multiplication over addition. For step 2, it's the same thing, distributive property of multiplication over addition again. Step 3, we have the commutative property of addition, that order doesn't matter. So we have, they have not yet here. I'm going to pause this. There we go. And then we have the commutative property of addition, reordering these middle terms. Exponents. So just as multiplication is repeated addition, exponents are repeated multiplication. That's all they are. So the number you're raising to a power is always called the base, just like other bases. We say base 10 because our number system, all of our place values have 10 as the base. 10 to the 0, 10 to the 1, 10 squared, 10 cubed, and so on. A to the first is always just A, so any number to the first power is always that number. If we have the same base and we're multiplying them together, we add the exponents. If we have a base and we're raising a power to another power, we multiply the exponents. If we have two different bases but they're raised to the same power, that's the same as the product of those numbers raised to that power. So in other words, what this is telling us is if we had, let's say, 3 to the 4th times 7 to the 4th, different bases, same power, that is the same as 3 times 7 to the 4th. And we could show that using a calculator. So we see here we've done 3 to the 4th, that's 81. 7 to the 4th is 2,401. When we multiply those numbers together, we get 194,481. And if instead we take 21 to the 4th, which is 3 times 7, we also get 194,481. Again, this only works if the exponent is the same. It does not work if the exponent is different. And we know if we divide, we subtract the exponents. So 4 to the 3rd minus, or divided by 4 to the 1st, or just 4, equals 4 squared, or 16. So if, for example, here we have some problems, we want to write the following with using just one exponent. So all of these are powers of 2. 8 is 2 cubed and 16 is 2 to the 4th, and we can use that as we do this. So this would be the same as 2 cubed to the 5th, 2 to the 4th to the 3rd, which is going to be 2 to the 6th times 2 to the 15th times 2 to the 12th. And now we have the same base, and we have our exponents simplified, so we can just add the exponents, and we get 2 to the 33rd. Exponents are usually middle school math. I believe sometimes they might show up in 5th grade also. And of course, it just kind of depends on where you teach, whether or not 6th grade or 5th grade is considered part of middle school or not. But again, one thing we want to work with exponents and other things is understanding where our students are going after they leave our class. It's important we know the whole structure. I know that sometimes people who want to teach kindergarten or 1st grade question why they're learning college math if they're teaching kindergarten or 1st grade. If it makes you feel better, people who are teaching freshmen in high school who are going to teach nothing beyond Algebra 1 or maybe geometry often ask questions like, why do I have to take multivariable calculus and differential equations? And the answer is the same. In both cases, you want to know where your students are going and you want to understand more thoroughly the math you're teaching them. And so in both cases, we learn far more, hopefully, than we teach. And we learn more, of course, as we teach. So there are different multiplication algorithms out there. Here is a multiplication algorithm that uses base 10 blocks to make it a little more visual. So 13 times 3, and sort of recognizing that we could say this is both 3 groups of 13, which is a total of 39, and then sort of just helping students recognize how that is as we move towards the standard algorithm. This is not yet the standard algorithm. In general, it's relatively easy to multiply by powers of 10. To multiply by 10, replace each piece with a base 10 piece that represents the next higher power of 10. We replace each unit with a long and replace each long with a flat. So multiplying by 10, we replace the long with a flat, the unit with a long. We also will teach multiplication using expanded addition. So on the left-hand side, you have expanded form and exponents being used. You might not use exponents. Now, I want you to use exponents in this course because you are college students. However, in your classrooms, your future classrooms, you might not use exponents. You might instead say times 100 times 10 times 1 and represent it that way. On the right, you see another way that is sometimes used. This is not yet the standard algorithm, but it's close to it. So we start by taking 7 times 4, and we see that that is 28. We write that down. And then underneath, what we do is now say 60 times 4 is 240, and we write that down. And then 300 times 4 is 1200, and we write that down. And then add our results. Again, here's an example with base 10 blocks of multiplication with a 2-digit factor. So 23 times 14. So what we have here is we have a representation of 23. And then down here we have or rather than just saying up here across, we have 23. So think of this as 10, 20, and 3. Now you're asking yourselves why I'm using flats rather than rods and longs rather than flats. That's because that relates to what we did previously when we just multiplied everything by 10. And then down the side we have 10, 14. And then when we do this and count all the pieces together, we find, and if we were doing all sorts of trading and stuff, we would end up with 322. This is time intensive in your classroom probably. It takes practice. It takes practice as you as a teacher to do it as well, but it can build student understanding of what's going on and help them get towards that standard algorithm. I mentioned lattice arithmetic before, or lattice addition rather. Lattice multiplication is much more commonly taught. It's much more useful, in my opinion. It's probably the most common alternate algorithm taught, and it's something that I know I've seen on praxis type exams, so it's something you should be familiar with. What you do is you write, it doesn't matter what number goes where, you write one number along the top, you write one number along the side, 14 by 23, or you could put 23 by 14. It doesn't matter what number goes where. It works just as well if you have 3 digits or even 4 digits. Usually you don't see them with more than 3 digits though. And then you first make boxes, so you have columns and rows, and then you draw a diagonal line through each box. You then multiply each box. 4 times 2 is 8. Since it's 8, you put a 0 in this. So this is really 0, 8. That's, again, the hardest part for kids to do. 1 times 2 is 2. The 2 goes here. The other box is a 0. 4 times 3 is 12. 1, 2. 1 times 3 is 3. 0, 3. Then we add diagonally. So 2 becomes 2. 8 plus 1 is 9, plus 3 is 12. There's my 2. I carried the 1. That's where this little 1 here comes from. 1 plus 2 is 3. 14 times 23 is 322. Again, we aren't going to do other bases in this class for multiplication. It's in your textbook if you want to learn about it. There's resources you could find online too. I think it's important you can add in different bases if you had to. I don't think it's important that you have to be able to multiply in different bases, personally. I do think some mental math is appropriate, though, which is not that slide. Sorry, I'm looking at the wrong screen. One idea is front-end multiplication. So in this example, we have 78 times 4. And so by front-end multiplication, we first take 70 times 4. That's 280. Then we take 8 times 4. That's 32. We add those together, and that becomes 312. That also can be a strategy, of course, for just doing it by hand, even if someone doesn't have the standard algorithm yet. We can also use compatible numbers. So if I'm multiplying 2 times 8 times 5 times 40 times 5, we can use our associative and commutative rules to regroup those into numbers that are easier to work with. So I'm going to regroup those, and anything ending in 0 is usually fairly easy to work with. Powers of 10 are easy to work with. So one way I could regroup this is eventually get to 10 times 200 times 8. So 10 times 200 is 2,000. 2,000 times 8 is 16,000. That's not necessarily the only way you could do it. There's always other approaches you could do. I could have done 5 times 5 is 25. 25 times 2 is 50. 50 times 8 is 400. 400 times 40 is 16,000. But when we say compatible numbers, we just mean numbers that multiply together to get numbers that are easier to work with. So again, there's more than one right way to do it. Sometimes thinking about money will help. So here we could think of this product as 84 quarters. So if we had 84 quarters, and that would mean that we would have $21, which would be the same as 2,100 cents, which is the answer to this particular problem. And then front-end estimation. We start by multiplying at the front. 400 times 9 is 3,600. And then 70 times 9 is 630. We add the two numbers together to get 4,230 as our estimate. We could keep going and say, oh, we're going to add 36 to that. That's also okay, but that's not an estimate anymore. Okay. We can also quickly estimate, round, and multiply and say, oh, well, 500 times 9 is 4,500, so my answer is going to be a little less than 4,500. It also works the opposite just by rounding down. I know that my answer can't be less than 3,600. It's going to be more than that. So you can sort of narrow down your choices. When you take your methods course, you will learn more about the different algorithms that exist, as well as learning how to teach the standard algorithm. That is always our eventual goal. On your homework problems, you're going to be asked to use some of the alternate algorithms that are introduced in this section. You have to use them. You cannot just give me the answer in the standard algorithm. I know you can do the standard algorithm or that you can use a calculator. You need to be able to show step by step in the algorithms what you're going to do. So that becomes very important in all of these problems in the homework. So I hope this will be beneficial for you. If you have any questions, please let me know.